So guys, today we are starting our series on dental materials. So we'll start with the properties of dental materials. Now again, what are dental materials actually? So dental materials are an integral part in dentistry. So these materials are used in prevention, restoration and rehabilitation. So these are the three important aspects in dentistry as such. And in each of these procedures, dental materials do come in play. So if you want to classify these materials, you can classify them into preventive materials, which are mainly going to be a pit and fissure sealants, which is used for prevention of onset of a dental disease. Next will be the restorative materials. So these are something we always play with. So it is used to repair or replace a tooth structure, which is most common examples will be your amalgam and composite. Again, auxiliary materials. Now, auxiliary materials actually do not play an important role as such, but they help in fabrication process. Like it does not form a part of a restoration, appliance or prosthesis, but it helps us in fabricating these things. For example, is gypsum or impression material. So, to make a removable partial denture, you need to first take an impression. So, for that you need an impression material. Once the impression is done, then you need to form a cast, for which you need your gypsum products. So, these are the different types of dental material that is available. So, now the properties of these dental materials. So, they can be broadly put as physical properties and biological properties. So, today we are going to focus mainly on the physical properties. Before going into dental materials as such, let's talk a little bit of matter and bonds. Now, matter is anything around you is made up of matter. Even the smallest speck in the universe is made up of matter. So, there are three forms of matter, mainly gas, liquid and solid, based on the difference in the energy. That is, you have one molecule or a matter, and this is made up of numerous or infinitesimal, that small amounts of atoms. So now these atoms again are made up of protons, electrons. So these protons or the positively charged components are kept inside the nucleus, whereas the electrons orbit around this nucleus, around the nucleus, like as with your solar system. Now, interatomic bonds. Now, these atoms are held together by means of certain forces. These are the interatomic forces or your bonds. So, how do you classify these bonds? So, these bonds can be classified either into primary bonds, which are chemical in nature. They are ionic, covalent or metallic bonds. And then you have your secondary bonds, which are your van der Waals forces, which are weaker and more physical rather than a chemical bond. So let's briefly see what each of these bonds are about. So first is ionic bonds. So these are the most simple chemical bonds. So these are formed by attraction between a positively and a negatively charged molecule. Now, one thing you should know is that for any molecule or an atom to be stable, its valency should be satisfied. So, apart from the first orbit like this one, every other orbit needs 8 electrons in it to become stable. So, what happens is these atoms either share these valence electrons or just give one valence electron to another atom to be stable. So, metallic ions most commonly have the tendency to just give off their valence electron to become stable, whereas non-metallic molecules like chloride or oxygen, all these things accept valence electrons and become stable. So, an ionic bond, a metallic atom, for example, I'll talk about sodium chloride. So, sodium has an atomic number of 11. So, when you draw the atomic structure or this atomic composure, you'll understand that there is only one valence electron in the outermost or the third orbit, which makes it unstable. When you talk about or when you see a chlorine molecule, so in this atom, the atomic number is 17 and in the outer valence, there is only 7 electrons. So it needs one more electron to become stable. So what happens is the sodium will give off this outer valence electron to chloride, thereby making it a stable, becoming stable by itself and making the another chlorine atom stable. So this is how a positively charged sodium and a negatively charged chloride combines together and form sodium chloride, both becoming stable by itself. This bond thereby forming between these two atoms is a ionic bond. Now next one is the covalent bond. So here what happens is the valence electrons are shared between the atoms. So let's see methane. So methane is a hydrocarbon wherein the carbon is forming valence, it is sharing its valence 4 valence electrons with 4 hydrogen atoms. So it has an atomic number of 6, thereby 4 unbalanced or unstable valence electrons are seen in its outermost orbit. So hydrogen atom has an atomic number of 1. So it has only one single orbit and one unbalanced or unstable valence electron. So each of the hydrogen molecule is going to share its outer valence electron with the carbon atom, thereby becoming stable themselves and stabilizing the carbon atom, forming methane. So this is what covalent bonds are about. Next are metallic bonds. Now these metals have a very characteristic property, which is the conduction of heat and electricity. So now how does this heat and electricity conduct in a metal? So the free electrons in these metals, like with this aluminum here, they will move among the atom or this metal lattice. So this allows the outer sheet electrons to be removed, making these atoms a positive ion, that is aluminium. So aluminium has 3 valence electrons in its outermost orbit, which is given off and making it a positive stable atom, that is Al3+. So here in this aluminum forming a metal lattice. So this aluminium has 3 free electrons which will be lost or will be released, thereby making it a stable structure. So this is what a metallic bond is about. Now van der Waals force is a secondary bond. So what happens here is that there is formation of a dipole. A dipole is nothing but an equal and oppositely charged or magnetized pole which is separated by a distance. Now here the main attraction or the force or the effectiveness of the bond or the strength of the bond is determined by the distance between the molecules. That is, as the distance increases, it becomes unstable. So it is not a chemical bond. Like I said, it's entirely a physical one. Now it is a very weak bond in comparison to your primary bonds. Here it is susceptible to disturbance. It's greatly susceptible to any form of disturbance which is going to disturb the formation of the dipole. Again, when the distance between the molecules increases, the force actually becomes weaker. And finally, this force will vanish, allowing these molecules to become separated and no longer related to each other. So I'll talk about these two chlorine. So these two molecules have some form of kind of a dipole existing between them. Now, as the distance between these molecules reduces to around 5 mm, they start developing this van der Waals forces and starts to get attracted to each other. So this is not what exactly happens, I'm just putting it for pictorial representation. So in simple term, this force can be either attraction or repulsion as well as any of the other intermolecular forces. Now, as the distance decreases, the polarity as well as the slight attraction or repulsion, whatever it is, it will also take place. Next is surface tension. So the surface tension is the main reason why you see soap bubbles on a surface of water when soap is mixed with it. So what is happening here is that typically the energy on the surface of a crystal or a solid is going to be so much higher than that within it. Why? Because the energy is more on the crystal lattice because there is no atoms on the outer surface and all of these atoms are present on the inner surface. And these atoms inside are all attracted equally to each other. Now here, when the interatomic distances are equal, the energy required to keep them in that position is very minimal. Now these atoms on the outer surface, they are constantly pulling the outermost atoms inside, thereby producing a tension on the outer surface. See, each of the atom is going to pull the remaining atoms towards itself, thereby dragging them, like forming some kind of a tension or energy inside. So now, the energy that is actually required to pull these atoms away. So I told you the surface energy is more than that on the inside. So the amount of energy actually required to drag these outer atoms towards the interior surface is going to be very high. So now this energy or the increased energy per unit area of the surface required to pull them together is what you call as the surface tension. So it's a very good example is, like I said, on surface of water there will be bubbles forming. These bubbles are formed because the innermost atoms pulling the outermost atoms towards them, thereby forming the beautiful round shaped bubble. Next is wetting. So simple term, wetting means putting water or a liquid between something and just immersing it in the liquid. So here, when you're taking two solid surface, it's very difficult to adhere to each other. Even if they look very smooth to naked eye, at a microscopic level they may have lots of surface irregularities which interfere with their adhesion. So ideally the distance between two surface molecules should be less than 0.0007 micrometer for proper adhesion. So it's very impossible, it's very difficult to achieve that kind of a micro-dimensional distance. So how can you actually tackle this and like attach or adhere these two structures? So when you use a fluid or a liquid which flows very nicely in this crest and trough, you can use the help of that molecule to bond them together. So when I'm putting a liquid which very nicely interacts with both of these molecules and flows in between these irregularities, it will facilitate the adhesion of these two molecules. This is what you call as wetting. So now, when the area of contact increases, the strength of adhesion increases. Next is contact angle. So in this wetting, there is an angle that is formed between this adhesive molecule and the adherent surface. This is what you call as a contact angle. So the contact angle formed will determine the extent of wetting of that particular structure. So now, when this liquid is spreading completely over the adherent surface, the angle thereby formed is going to be 0 degree, and this is what you call as a complete wetting. This is what you see when water is poured over a soapy surface, or the other way around, it will completely spread on surface and forms a complete wetting. What if the liquid is not flowing fully? So it can either form somewhat good wetting, like a partial wetting, or it will give a bad wetting which is like does not flow at all, just forms a separate ball or a bulb drop on top of it, which is the case with oil, miscible liquids like oil and water. Now let's talk about the physical properties. So we'll just see half of these properties today and half will be discussed in the next video. So first and foremost is going to be stress. I'm not talking about like exam stress, I'm talking about stress in a molecule. So the internal resistance of the body to an external force. The force, a kind of a force which is equal and opposite to that of the external force, that is stress. This can be such an extent that it will result in the deformation of the molecule on which this force is acting upon. Now, stress is always defined in terms of an external force. Why this is being described like this? Why not internal force? This is because the internal force is impractical to measure, and on the other hand, your external force can be very easily measured. Now, the significance come in case of restoration. So, we know that the restorations are given on a very small surface area or unit per surface area. So, it should be able to withstand the force that is acting on without any deformation or fracture. So, mathematically we can represent stress as force per unit area, so which is put as F by A. Now there are three types of stress. So you have tensile stress, compressive stress and shear stress. So what is each of these? So tensile stress is when two set of forces are present which are acting away from each other, literally pulling the material. So now when this goes beyond the tolerable level, it will result in the elongation or stretching of that particular material. Next, we'll talk about the compressive stress. So here, the two sets of forces are facing or moving towards each other. So when it happens like that, it is going to compress that particular material, resulting in the shortening of the body. Next is shear stress. Here, two forces are directed parallel to each other. So this can result in either twisting of the body, or it can actually result in the thing getting split and moved into two portions. So this is what happens with shear stress. Now there is something called as complex. See, when you apply force over a body, all the three types of stresses are present, but one will be more than the remaining. For example, a wire is being stretched. In such a case, all three, that is the tensile stress, shear stress and compressive stress will be there, in which one may predominate the other. Next, let's talk about strain. So strain is something that is going to happen in response to stress. That is, it is the resistance to deformation. That is, when a stress or a force is given, the body has a tendency to deform. So that resistance of the body to this deformation is what you call as a strain. So again, mathematically, this can be represented as deformation in length. That is the amount of difference in length that is achieved by the stress divided by the original length. Next is Poisson's ratio. So this Poisson's ratio is said to describe Poisson effect, which goes by deformation of the material will occur in the direction perpendicular to the force. So when a force is given in this direction, the deformation is going to occur in a direction perpendicular to it. So the deformation can be either expansion or elongation, or contraction or shortening. Now, this change in the dimension, it can happen to the width, which is what you call as a lateral or a transverse strain, or this change can happen to the length of the material, which is an axial or longitudinal strain. So now, Poisson's ratio can be described as a ratio of change in the width per unit of material. That is a ratio of your lateral or transverse strain to that in the change in the length per unit length as a result of strain, which is nothing but the axial or longitudinal strain. So here you have a block of a material which, when you're giving a lateral as well as axial strain, it's going to form some kind of a deformation. So this deformation, or the ratio of these deformations in both the plane, is what is called as Poisson's ratio. So it is just a ratio of transverse strain with axial strain. Next, we'll see the stress strain curve. So stress strain curve is a graphical representation. So this is a graphical representation to see the relationship between stress and strain. So how do you determine it? So now it is determined by applying load on the test material, and then the deformation is used to determine the stress and strain produced in that particular case. Again, in addition to determining stress and strain, you can also determine the Young's modulus, yield strength and the ultimate tensile strength. So these molecules will be dealt in the next video. Now, graphically, it will be represented like this. So, from this graph itself, you can see a lot of materials can be determined. So, you can determine the stress, the strain, the proportional limit, elastic limit, yield strength, ultimate strength, fracture. All these things can be determined. So, the amount till which it will be elastic, amount till which it will be plastic, and the point after which it is going to fracture. All these things can be determined with this simple graph. So let's talk about proportional limit. So proportional limit is it's a point where stress is it is a maximum value till which stress is going to be proportional to the strain. So here there is something called Hooke's law. So Hooke's law states that a stress of a material is proportional to its applied strain till the elastic limit. That is, stress is always proportional to the strain till the range of the elastic limit. So in simple terms, I'll tell you, proportional limit is the maximum stress beyond which the material is going to be deformed. That is, when this simple philosophy works with orthodontic springs, which use for expansion. So when stress is less than or equal to proportional limit, there is not going to be any deformation of the material. But again, if the stress increases beyond the proportional limit, there is going to be plastic deformation of the material. So in your stress strain graph, this proportional limit is going to be represented by the straight line portion of the graph, gradually increasing up to the elastic limit. So now, what is this elastic limit? So it is a maximum stress. So a proportional limit means a maximum extent till which it is going to be it is not going to undergo plastic deformation. So elastic limit is the maximum stretch till which it can withstand the force without deformation. So it is a point till which a proportional limit is going to be there. Now beyond this, the material will be deformed permanently. That is represented by the plastic limit. So next is yield strength. So yield strength is a stress at which the material will exhibit limiting deviation from, that is, it is a point beyond a proportionality limit where stress is no longer proportional to the strain. So it is a limit of tolerable permanent strain. Now there is an arbitrary value called offset, which represents a percentage of exhibitable permanent deformation. That is, when I am plotting a stress strain graph, I am going to give it a value of 10 or 20 as offset. So that is the value of accepted permanent deformation, which is represented by your yield strength. So I am going to plot a line parallel to this my y-axis in the stress strain graph. So the point where this offset is going to meet the stress strain graph is going to be represented by the yield strength. Next is modulus of elasticity. So modulus of elasticity is nothing but the ratio of stress to strain. So it is also called as elastic modulus or Young's modulus. Now this represents the relative stiffness or rigidity of a material within its elastic range. Now this modulus of elasticity, so I told you it's a ratio of stress to strain. So we know that stress or strain is represented by force per area and elongation by the deformation by the normal length. So I can say that it is going to be product of force and length divided by the degree of deformation into the area on which the force is going to act upon. So from this we can deduce that it is directly proportional to the stress acting on the material and indirectly proportional to the strain experienced by the material. So the significance of modulus of elasticity comes in case of the metal frame in a metal ceramic bridge. So if the metal ceramic bridge or the metal frame is not stiff, it can easily undergo fracture, thereby resulting in the failure of your FPD material. Hey guys, if you have any doubts pertaining to this particular topic discussed today, please do leave us a comment or you can DM us in our Instagram page. And please don't forget to stay tuned to our Instagram page, because from tomorrow onwards, we'll be putting NEET related entrance questions in our Instagram page related to the videos that we are putting the previous week.